Session we will learn how to determine the effect of gyroscopic couple on four-wheel vehicle. Now the condition to be satisfied by four-wheel vehicle while it is moving along a curved path is that no wheel should be lifted off the ground while taking a turn. Okay. And this is possible only when the vertical reactions of the ground on the wheels are always positive. That is, they are acting upwards. Now, to study the stability of four-wheel vehicle moving on a curved path, we'll make one assumption that wheels and engine parts are rotating in the same plane and in same direction. Because this is important, effect of gyroscopic torque will change when the wheels and engine parts are rotating in opposite direction or they are rotating in different planes or the planes which are not parallel to each other. So you'll remember this assumption. We are assuming that wheels and engine parts are rotating in same direction. Suppose the vehicle is moving in forward direction, so wheels will turn this way, and we assume that engine parts also are rotating in the same sense, like this. Now the velocity with which the wheels rotate, we'll call it as omega, and the velocity with which the engine parts rotate, we will call it as omega e. Let us suppose that the CG of the vehicle is located at the distance of h from the rails or ground surface. Now the main task is to find out the reactions offered by the ground on all the wheels due to the weight of vehicle, due to gyroscopic couple and due to centrifugal couple while the vehicle is taking a turn. The first of all, we'll find out the reactions offered by the ground on the wheels due to the weight of the vehicle. We will again assume that the weight is equally divided over the four wheels. Under this condition, weight on each wheel will be total weight divided by 4, that is equals to mg by 4. And this weight will act in downward direction. Now equal and opposite reactions will be offered by the ground on each wheel. So we'll call that reaction as Rw, reaction offered by the ground on each wheel due to the weight of vehicle. Rw is equals to W by 4, that is equals to mg by 4. Now these reactions will be upwards, opposite to the acting force. The force exerted by each wheel on the ground will be downwards, and the reactions offered by the ground on each wheel will be upwards. And magnitude of that reaction is W by 4. So we'll represent these reactions on each wheel due to the weight in the diagram using upward arrows. The next, reactions offered by the ground on each of the wheels due to gyroscopic couple. Now let us suppose that the vehicle is taking a left turn with velocity of omega p. This is precision motion because when the vehicle is taking a left turn, it will change the direction of axis of rotation of the wheels as well as axis of rotation of engine parts, hence producing the gyroscopic torque. So we call such motion as precision motion. So the vehicle is taking a left turn with a velocity of omega p, precision velocity. Now when it is taking a left turn, it will change the direction of axis of rotation of the wheels and direction of axis of rotation of the engine. So there will be two gyroscopic torques acting on the vehicle while it is taking a left turn. First one, we will find out the reactions offered by the ground due to gyroscopic couple because of rotating wheels. we know that magnitude of gyroscopic torque is given by I omega omega p. Here Cw indicates the gyroscopic torque due to the wheels. Iw is moment of inertia of each wheel, omega w is the speed of each wheel, and omega p is the precision speed. We multiplied this equation by 4 because there are 4 such wheels. So I omega omega p is the gyroscopic torque produced by each rotating wheel, into 4 will be the gyroscopic torque as a result of 4 rotating wheels. We find out the angular speed of each wheel by using this equation, which is equals to linear speed of the vehicle divided by radius of each wheel. And we find out the precision velocity omega p using this equation, linear speed of the vehicle divided by turning radius. The next is gyroscopic couple due to engine. We use the same equation, C is equals to I omega omega p. CE indicates the gyroscopic torque due to engine rotating parts. IE is the moment of inertia of the engine rotating parts. Omega E is the speed of engine parts or speed of engine, and omega p is the precision velocity, which is equals to V upon turning radius. Now if G is the gear ratio between engine and the wheels, so G will be equals to WE upon omega E upon omega W. You will remember that G is always greater than 1. So engine speed is always greater than the speed of wheels because we reduce the speed using transmission system. So you will always write the equation for G as engine speed divided by wheel speeds. Wheel speed. So using this, we will eliminate this W omega E. Okay. So we get CE is equals to IE into G omega W into omega P as the gyroscopic couple due to engine. Now if we assume that the wheels and the engine rotates in parallel planes and in the same direction, we can add these two couples to find out the net gyroscopic torque. What I said, we are assuming that the engine and the wheels are rotating in parallel planes. Then we can find out the net gyroscopic torque as the algebraic sum of these two couples. So net gyroscopic torque Cg is equals to Cw plus minus Ce. We will use the plus sign when wheels and engine parts rotate in same direction, and you will use the negative sign when wheel and engine parts rotate in opposite direction. This is valid only when the wheels and engine rotates in parallel planes or the same plane. If engine parts or engine and wheels rotate in non-parallel planes, you cannot add or subtract these two. Okay. In that case, you will find out the magnitude of all the couples separately. Okay, CW and CE, and their effects also counted to be separate. Now, net gyroscopic couple is CG while taking a left turn. Let us find out the effect of this gyroscopic torque on the vehicle. Say this is, we'll consider one of the wheels. We are looking from the rear side of the vehicle. This is the axis of rotation of the wheel. When the vehicle is moving in forward direction, the wheels will spin in this sense. We call this as spin angular velocity. Now we find out the spin vector using right hand rule. We curl the fingers of right hand in the sense of omega, and the thumb will point in the direction of spin vector. So this is our spin vector. Now the vehicle is taking a left turn. Now when the vehicle takes a left turn, this axis will change its direction like this. This vector will take the new position like this. And the direction of active gyroscopic torque is perpendicular to the spin vector, and it will act in the direction of change in the direction of this spin vector. Reactive torque is opposite to the active torque. We indicate it by CR. Now all this is happening in horizontal plane. This is visible in top view of the vehicle, because the vehicle is steering towards the left in horizontal plane. So plane of precision is horizontal plane, which is visible in top view. So all these vectors are displaced, or this is happening in horizontal plane. So now this is the vector representing CR. We want to find out the sense in which this CR acts. For that we make use of right hand rule. Hold this vector in the right hand such that the thumb is pointing in the direction of arrow. The sense of the fingers of right hand will give the sense of CR. So now when you hold this vector in your right hand such that your thumb is pointing in the direction of arrow, your fingers will curl this way, and that is the sense of CR. Okay. Now we are looking at the vehicle from rear side, and this is happening in horizontal plane. That means when you look from the rear side, CR will act from left to right of the vehicle like this. So this is the sense of reactive gyroscopic torque. It is acting from left to right of the vehicle. So clockwise as seen from the rear side. Now you can find out the sense of CR using another method. Make use of coordinate system. Place the object, that is a four-wheel vehicle, along the x-axis. This is spin angular velocity omega. To find out the spin vector, we turn the fingers of right hand in the direction of omega, and thumb will point this way, which represents the spin vector. So we place the spin vector at the origin. Next, the vehicle is taking a left turn with the velocity of omega p. We identify the precision plane in which omega p acts, and that plane is XOZ. The vehicle is taking a left turn in horizontal plane XOZ. So omega p acts in plane XOZ. Now to find out the precision vector representing omega p, we take the right hand in the precision plane XOZ and curl the fingers of right hand in the direction of omega p. Thumb will point upwards, and that is the direction of precision vector. What we do, we take the right hand in the precision plane XOZ, we curl the fingers of right hand in the sense of omega p, thumb will point in the direction of precision vector. So in this case it is going upwards, so precision vector will act along OY. Next we find out the active gyroscopic torque vector, which is obtained by rotating the spin vector OZ by 90 degrees in precision plane XOZ in the direction of precision velocity omega p. So if we rotate the vector OZ, spin vector, by 90 degrees in the direction of omega p in precision plane XOZ, we get the active gyroscopic torque vector along OX. Reactive torque will act opposite to the active torque. So reactive torque will act along OX dash. To find out the sense of reactive torque CR, we make use of right hand rule. For that, we will hold the vector representing CR, this vector OX dash, in right hand such that the thumb of right hand is pointing in the direction of arrow, and the signs of the fingers will give the signs of CR. Now when we hold this vector CR in right hand, your fingers will be curved this way, and that is the sense of CR. Okay, so this is the sense of CR according to right hand rule. Now the plane in which CR acts is the plane perpendicular to its vector. The plane perpendicular to vector OX dash is plane YOZ. So CR acts in plane YOZ. And the effect of this CR on the vehicle will be, it will try to overturn the vehicle from left to right. So CR is acting from left to right as seen from the rear side. So this is the rear view. So we'll represent CR about CG here. It is acting from left to right. Now if CR is there, CR is provided by or will produce vertical forces on outer and inner wheels, vertical and parallel forces. Okay. Let this force be equals to Rg. Now here is couple CR, it will produce or is provided by the upward force acting on the left side of the vehicle and downward force acting on the right side of the vehicle. Okay. We call this reaction as Rg. So we can write this couple CR is produced by these forces Rg. So magnitude of couple CG is equals to Rg into distance between these two forces, that is W. So CG is equals to Rg into W. We want Rg. So Rg is equals to Cg upon W. This is reaction on two left wheels and reaction on two right wheels. Okay, Rg is equals to Cg upon W is the reaction offered by two inner wheels and two outer wheels. Therefore, reaction on each of the inner wheels and each of the outer wheels will be is equals to Cg upon twice W. Okay. There are two wheels on left side and there are two wheels on right side. Rg is the total reaction on left side and Rg is also the total reaction on right side. So divided by 2 will be the reaction on each of the inner wheels as well as each of the outer wheels. Now on each of the inner wheels, this reaction Rg is acting in upward direction. Okay, and reaction offered by each of the outer wheels is downwards. Now these are the reactions or forces exerted by each of the wheels on the ground surface. Now the ground surface will exert equal and opposite reactions on the wheels. So reactions of ground on each of the wheels will be same in magnitude but opposite in direction. Okay. On each of the inner wheels, the reactions offered by ground will be downwards, and on each of the outer wheels, reaction offered by the ground will be upwards. Okay. Remember that these reactions marked in circles are the forces exerted by each wheel on the ground. So the ground will exert equal and opposite reactions. Let us mark these reactions in the diagram. Rg downwards on inner wheels and upwards on outer wheels, like this. Rg downwards on inner wheels and upwards on outer wheels. So these are the reactions on each of the wheels due to gyroscopic torque produced by rotating wheels and rotating engine parts. The last one is reaction due to centrifugal couple. When we take the left turn, centrifugal force will act at Cg towards the right. Okay, and it will magnitude of that centrifugal force is equals to mr omega square, where omega is the speed with which the vehicle is taking a left turn, and that is equals to omega p, precision angular velocity. So m, the mass of the vehicle, capital R is the turning radius, and omega p is the speed with which the vehicle is taking a turn, angular speed, that is precision velocity omega p. So Fc is equals to mr omega p square. Now this centrifugal force will produce the couple whose magnitude is equals to Fc into h. So this force into this distance will produce the centrifugal couple Cc in this sense, right? Now this will tend to overturn the vehicle outwards. Now to avoid this, balancing couple will be produced opposite to Cc. Okay. So if this is Cc, balancing couple will be produced opposite to this by this forces Rc. So magnitude of balancing couple will be Rc into W. Therefore, Rc is equals to Cc divided by W on two inner wheels and on two outer wheels. Rc on two inner wheels as well as on two outer wheels. Therefore, the force on each of the inner wheels and on each of the outer wheels will be divided by 2. So, reaction offered by the ground on each of the inner wheels will be downwards, and on each of the outer wheels will be upwards, opposite to this couple. You will remember one thing, if this is the rear view and this is the sense of couple, so this is the net gyroscopic torque, you will directly mark the reactions offered by the ground on the wheels opposite to this couple. So this will be upward and this will be downward. Couple is going this way, so you have to produce the reacting couple offered by the ground, and that will be produced by opposite forces. The same thing for centrifugal couple. If centrifugal couple is acting like this, you will mark the forces such that it will produce the opposite couple, balancing couple. Okay. So here I have shown Rc downwards on inner wheels and Rc upwards on outer wheels. Reaction offered by the ground on each of the wheels due to centrifugal couple. Now let us find out the total reactions on each of the wheels. So total reaction on each of the outer wheels. Reactions on both the outer wheels are acting upwards, all the reactions, so we can add them, Rw plus Rg plus Rc. So of course their summation will be positive and net reaction will be also positive. So Ro is the total reaction on each of the outer wheels and it will act in upward direction. Now let us find out the total reactions on each of the inner wheels. Ri, reaction on each of the inner wheels, is equals to Rw, positive, is acting in upward direction, minus Rg, negative, minus Rc, negative, acting in downward direction. Okay. Now we cannot predict whether Ri will be positive or negative, but there is a possibility that it may become equals to 0 or fall to negative value, and when this happens, inner wheels will leave the ground while the vehicle is taking a turn, and that is not desirable. Ri should be always positive in order to avoid the slip. Okay. So for this case, which we have discussed, to avoid the overturning of the vehicle, Rw must be always greater than or equals to Rg minus Rc in order to avoid the overturning of vehicle. Now in this case, directions of the reacting forces on each of the inner wheels were same, as well as on each of the outer wheels were same. That's why we have only two equations. Reactions on each of the inner wheel will be same, and reaction on each of the outer wheel will be same. In case if these reactions are not same, you need to find out the reaction on each of the wheels separately. So there will be four equations, say R1, R2, R3 and R4. If directions of reactions for each of the wheels is not same, you will find out total reaction on wheel number 1, wheel number 2, wheel number 3 and wheel number 4 separately, and check whether are there any chances of negative reactions. Thank you.